Hey, welcome back to Short Takes 331. Today we're going to start our discussion of determinants. So this is determinants part 1. And recall that in a previous video we saw Cramer's rule as a way to solve 2x2 systems of equations. So here's our reminder of that. So suppose we have then this system of equations where we have our matrix A given by A, B, C, D. These are our unknowns x1 and x2, and this is our right-hand side y1 and y2. Now the determinant of A is of course just AD minus BC. And Cramer's rule tells us that x1 is equal to the ratio of two determinants, x2 is also equal to the ratio of two determinants. What goes on the bottom is always the determinant of A, but on top you have to replace this, in this A, you have to replace the first column with y1, y2, your right hand side, and for x2 you also take the determinant of A, but you replace the second column by y1 and y2. And you go ahead and calculate that, and that gives you the answer. Now it turns out that that holds for systems of equations beyond 2x2. This holds in general for the n by n case. But what we didn't see is how to calculate determinants in the general case of n by n. And so that's what we're going to see today. There's a recursive definition, which is the one I like. It's called the Laplace expansion. And it goes like this. The determinant of A is given by the sum from j equals 1 to n, assuming that A is an n by n matrix that looks like this. And A1j times minus 1 to the 1 plus j times the determinant of A1j. Now this A1j is itself a matrix, and is obtained from the original matrix A by removing the row I and the column j. So what does that mean? Well, suppose we look at the first term in this sum. So then j equals 1. So then we have A11 times minus 1 to the 1 plus 1, that's minus 1 squared, that's just 1. And then the determinant of A11, this big A11. And that means you have to remove the first row, remove the first column, and you're left with a submatrix of size n minus 1 by n minus 1. And so at that point, you have a determinant of a smaller matrix, and what you do is you go ahead and you reapply this rule. And then you go to the second term, and again, you do the same thing. So A12 minus 1 to the 1 plus 2, so that's going to be a minus 1 here. And the determinant of A12, again, you remove the first row, but now you remove the second column, and you're left with a submatrix that you can address by reapplying the same rule. And you go ahead and you go through all the elements of this row, and then you have your determinant. Now this was done for the first row, but you could have picked the second row or the last row or any row that you find convenient. And this is really nice because it may be that in some row you have a lot of zeros, and so you pick that row because then a lot of the terms will disappear and you'll be left with a simpler expression. So here's an example of how to do the 3x3 case, which we didn't see before. We only saw 2x2 cases in previous videos. And so for 3x3, your matrix looks like this. I call this matrix now M for a change. And so our elements are A11 all the way through to A33. And the result is then of applying this formula is A11 times M11. This minus 1 is elevated to the second power, and so it doesn't appear, there's no sign here at all. The M11 is from removing the first column, the first row, and you're left with this submatrix. And then we have minus, because we have minus 1 to the 1 plus 2, A12 times M12, the matrix that results from removing the first row and the second column. And then finally, A13 times M13, which is the submatrix that results from removing the first row and the last column. And so what we've done with this, and is we've accomplished that we've changed the 3x3 problem of calculating this big determinant into 3 2x2 determinants, which we know how to do from before. And so that's why this is a recursive definition. And so with this, armed with this definition, then you know how to calculate this determinant, and then automatically using Cramer's rule applied to the 3x3 case, you know how to solve 3x3 systems of equations. So you just take the ratio of two determinants, and to take the determinants of 3x3 cases, you apply this this definition. Of course, in a 3x3 case, compared to this one here, you would have 3 columns, you have 3 rows. And whenever we said replace the first column with the right-hand side, you have to do precisely that. You would have y1, y2, and then a y3, and you would do the same here, and there would be an x3 where you replace the last column with y1, y2, and y3. But other than that, you just calculate the ratio of two determinants like you do here, and now you would do it one more time. And the definition of the determinant will tell you then you have to go through this more complicated expression, but other than that is the same. If you enjoyed this video so far, please like and subscribe. If you're looking for a tutor in physics or math in English or in Spanish, you can contact me at shorttake331@gmail.com. Another definition that is very common and used a lot in physics and in field theory is that the determinant of A is the sum over these indices I1 through In from 1 to n of epsilon I sub 1, I sub 2, all the way to I sub n. This is called the Levi beta tensor. I'll tell you about that in a second, times this product of the elements of A. So the element A1, I1, A2, I2, all the way through AN, IN. So this is an element of the first row, this is an element of the second row, and this is an element of the nth row. And so what this is doing really is summing over all the possible permutations of this product with signs assigned to them. Because this Levi beta tensor is actually 1 if this collection of indices is an even permutation of 1, 2, 3 to n. If it's minus 1 if it's an odd permutation, and it's 0 otherwise. What's this otherwise? What does it mean? Well, if 2 of these indices are the same, for example 1, 1 or 3, 3 or what have you, then that will be 0 automatically. What do we mean by an even or an odd permutation? Well, that's actually also simple. Suppose that instead of saying 1, 2, 3, it said 2, 1, 3, then you flip the 1 and the 2 and you get the normal order 1, 2, 3, then that would tell you that the 2, 1, 3 case takes the value minus 1. So let's see an example of that for the most trivial case of, or one of the most trivial cases of epsilon ij. So when you have a matrix of size 2 by 2. So that tells us that epsilon ij is 1 if I is equals to 1 and j is equals to 2. This is the 1, 2 order, the normal order of the integers. Then minus 1 if you inverted the order, 2 and 1, and it's 0 otherwise if you have 1, 1 or 2, 2. Okay, and so what this does is it couples the crossed elements that we saw in the definition of the 2 by 2 determinant. Now you can study using these rules the 3 by 3 case, and so you can calculate easily that epsilon 1, 2, 3 has the normal order, so that's 1. And then if you flip the 2 and the 1, or the 3 and the 2, or the 3 and the 1, any single flip like that will produce an odd permutation, and so you have minus 1. And any indices that coincide here will lead you to a 0. So epsilon 1, 1, 3 or 2, 2, 1 or something like that will always give you 0. And so that then will catch all the permutations of these elements and with the appropriate signs. Now, keep in mind there are n factorial such permutations, and so we'll come back to that in just a minute. Keep that in mind. Now, useful properties of the determinant that tell us in some cases how to compute them are as follows. The most trivial case, in fact, that you can see from the definition, this last definition that we saw here, is that the determinant of the identity matrix is just 1. And this is very easy to see because the only elements that survive in the identity matrix are 1, 1 and 2, 2 and so on, and n, n. And so the only element that survives is 1, 2, 3 all the way to n, which is 1 for the epsilon. All the other terms in the sum will just vanish. And that is to say, from I1 you only survive the 1, from I2 you only survive when it's 2, and so on. And so all the other terms actually vanish, and so you're left with this expression, which is just 1, because the product of all those diagonal elements is 1. And the same applies really to any diagonal matrix. For any diagonal matrix, the determinant of that matrix is just the product d1, d1, 1, d2, 2, all the way through d and n. So it's the product of the diagonal elements. Another property that's easy to see from this expression is that if you multiply your matrix by a constant, then that constant will appear here and here and here and so on, because you multiply all the elements. And so that constant, let's call it c here, then it's c to the n comes out here, because you can grab c from each of those. It doesn't depend on any indices or anything, so it comes out as c to the n. And that's what I wrote here for a matrix M. So if you multiply the matrix M by c, then you get c to the n, determinant of M. A property that's much harder to prove, or at least a little harder to prove, but it's very useful, is that the determinant of A times B is the determinant of A times the determinant of B. So the determinant of the product is the product of the determinants if the matrix is square. So here we're always considering, for this whole video, square matrices. Now, what's not true in general is that the determinant of A plus B is the determinant of A plus the determinant of B. So this does not hold in general. It may hold in some cases, but for example, the trivial case where B is 0, then obviously it holds. But it does not hold in general, so you should be very careful. The determinant is not a linear function, and so of the elements of the matrix, and so you should be mindful of that. The determinant of the inverse of the matrix is the inverse of the determinant. You see here how we run into trouble when the determinant of the matrix is 0, then the determinant of the inverse would have to be infinity. Well, we know actually from a previous video that if the determinant of a matrix is 0, then its inverse doesn't really exist. And so, that's perfectly consistent. You can figure out how to take the derivative of a determinant if the matrix elements depend on a parameter. And it turns out that that derivative is equal to the determinant itself times this trace of A inverse times dA d lambda, if the parameter is lambda. And so that's how the derivative acts on a determinant. It goes through the determinant, but it enters with this product as a trace of A inverse dA d lambda. And finally, if you imagine taking the exponential of a matrix by using the Taylor expansion of the exponential, then it turns out that the determinant of that exponential is the exponential of the trace of the matrix. Now, a property that is very useful to understand, but I will not prove here, is that it turns out that if two rows or columns of the matrix are proportional to each other, then your determinant will be 0. And more generally, in fact, if two rows or columns, or actually the rows or columns form a linearly dependent set, of which the previous statement is a particular case, then the determinant of the matrix is 0. So you might remember from what we saw in a previous lecture, a previous video when discussing systems of equations, that if you have rows that are linearly dependent, then you have basically copies of the same equations, and that don't give you new information, and so that leads you to cases where you either have no solution or you have an infinite number of solutions, and that goes hand in hand with not having an inverse for the matrix representing your system of equations, and that's what's being expressed here. So if the rows or columns from a linearly dependent set, then your determinant will vanish. Now, in a more practical direction, it turns out that not only is the determinant of a diagonal matrix equal to the product of the diagonal elements, it turns out if your matrix is upper triangular or lower triangular, you can show, using the same definition that we discussed before, that the determinant is equal to the product of the diagonal elements. And this gives us really good handle on how to calculate determinants of a matrix without summing n factorial terms. That sum over n factorial terms can be really, really difficult to do, very challenging numerically, because n factorial grows very quickly if the matrix is very large. So if you have a matrix, as in real life, of size 100 by 100 or 1000 by 1000, you really don't want to go over 100 factorial or 1000 factorial terms to calculate the determinant. And even if you weren't able to do that, taking the product and doing the sums could be numerically very challenging. Now, the way to do this is to turn your matrix into a triangular form, if you can, or diagonal form. That would be even better if you can do that. And that way, then you can take the determinant by just doing the product of the elements in the diagonal. And it turns out that there's a way to turn a matrix into a triangular form by Gaussian elimination, and there are other ways to access diagonal forms of a matrix using matrix diagonalization, which is something I will see in a future video as well. So that would really be the best way to calculate your determinant rather than summing the n factorial terms. Now, as an application of determinants, I want to mention these multidimensional Gaussian integrals. We're not going to see exactly how to calculate them. I will just state the result, but this is how it goes. So if you have a multidimensional Gaussian integral that looks like this, and this is not esoteric, this actually appears in quantum field theory all the time, and so this integrals look like this. There's an integral from minus infinity to infinity for each of these variables, from 1 to x1 to xd, so we're in d dimensions. So imagine that there's an integral in front of each of these dx differentials, and we're going from minus infinity to infinity, and in the exponent here we have e to the minus x transposed mx, and this is what's called a quadratic form. It's a quadratic expression in x, and so our vector x looks like this, and our transpose vector looks like this, and they both have d components, and m is a d by d matrix. So then this product is perfectly well defined, and it's basically some linear combination, some quadratic linear combination of the x's with themselves. Now, this integral doesn't always exist. It depends on which m. Okay, so of course, if we're in d dimensions, we end up with a case where, if we're in one dimension, we end up with a case where the only way in which this integral exists is if m is a positive number. So then we have a nice Gaussian decay, and then the integral converges. Now, if we're in higher dimensions, that's not so simple. It's a bit more complicated, and you may end up with directions where the integrand doesn't vary at all, and so it's a constant. It doesn't decay at infinity. or worse, it could explode at infinity if the matrix M is not properly chosen. So if you end up with a matrix M that has this weird property, so then the integral won't exist. And here's an example of that. An example that works is if M is just 1, 1, so then the sum of the exponent is e to the minus x1 squared and then minus x2 squared, and so both decay, and so both are fine. But if you have minus 1 and 2, then the 2 will be okay, but this minus 1 will give us e to the plus x1 squared. And so that will, so this minus sign will cancel with this minus sign, and then will be explode at infinity. And so of course the integral diverges. So not every matrix is okay. It turns out that this matrix M could be complex as long as it has some properties of its real part, and this is something we'll discuss in a future video where we see how to really do these integrals in detail. For now, I'll just state the result, that it turns out that this integral, when it exists, is actually equal to pi to the d divided by the determinant of M, everything to the power 1/2. So you see the determinants then enter in these very important integrals that are all over physics. That's all I have for you today. I hope you enjoyed this video. If you did, please like and subscribe. If you need a tutor in physics or math in English or in Spanish, you can contact me at shorttext331@gmail.com, or you can leave a comment in the comments section below. And I'll see you next time.